A modern business operation is chaotic. Logistics centers manage thousands of simultaneous sales, scattered customer records, and moving inventory in real time. Computers cannot natively process that multidimensional reality. Hardware requires strict mathematical order. To bridge that gap, architects construct a data model. This is the strict logical structure that translates real-world operations into a format machines can read and compute. Without this translation, millions of raw data points remain completely inaccessible to the organization. Mastering this structural translation is the foundational skill required for database design and modern business intelligence. The software engine responsible for housing this information is a database management system, or DBMS. A DBMS performs exactly 4 operational functions: creating, reading, updating, and deleting data, while simultaneously controlling network access and security. Today, the industry standard framework for these systems is the relational database model. The relational model forces complex, multidimensional information into logically related 2-dimensional tables. Organizing data into these 2D grids allows the system to link records through shared keys, which simplifies the logic needed to retrieve specific subsets of information. The most basic architectural unit of this relational model is the entity. Often referred to as a table, an entity is a dedicated storage unit for information concerning a specific person, place, thing, transaction, or event. This diagram illustrates 4 distinct business entities: customer, order, item, and distributor. Beneath each header are vertical lists of data elements. These elements are attributes, providing the descriptive characteristics of the entity. Different entities possess entirely different attributes. Entities establish the primary subject of the data, while attributes supply the necessary descriptive details required to execute business logic. Not all attributes are structurally equal. Some contain hidden complexities that can break a database. This flowchart isolates the address data. A full address in a single cell is too complex for efficient searches. Address is a composite attribute, dividing into smaller independent subparts. These subparts are simple attributes, which cannot be broken down further. Database architects must break composite attributes down into simple attributes. Doing so allows end users to execute highly targeted searches, such as querying all customers located within a single specific zip code. Databases must also handle information that changes over time, like a person's age. A stored attribute is a fixed piece of data permanently saved within the system. Here, a stored date of birth attribute feeds into a mathematical equation alongside the current system time. The result is a derived attribute. This data is not permanently stored. Instead, it is calculated on demand using stored attributes. Derived attributes save hard drive storage space and eliminate the need to manually update volatile data, like a customer's age, every single year. In contrast, null-valued attributes are essential system placeholders. They are deployed when a specific value is completely unknown, or when an attribute, like a mobile phone number, simply does not apply to that entity. Classifying attributes correctly ensures the database structure remains lightweight and allows the mathematics used in derived fields to remain consistent. Relational architecture relies on a hard rule. Systems require single-valued attributes. A data field can only hold one value at a time. Real-world logistics frequently break this rule. A single customer entity, for example, very often possesses multiple phone numbers. This graphic shows a database attempting to store multiple values in a single slot, causing the structure to split. The DBMS is forced to parse every entry to find a match, increasing computational load and limiting indexing efficiency. To restore order, multi-valued attributes must be entirely removed from the parent entity and placed into a new, dedicated entity of their own. This diagram shows the correct application of relational architecture. The core employee entity neatly branches outward to distinct, separately housed dependent entities via a one-to-many relationship. Real-world complexities must be fractured into completely new tables to maintain the processing speed of the database. The structural complexity escalates when we look at the relationships between entirely different entities. The absolute limit of the relational model is that while it easily handles one-to-one or one-to-many relationships, it cannot directly process many-to-many relationships. In a many-to-many collision, multiple Type A entities attempt to directly connect to Type B simultaneously. This crashes databases because relationships cannot hold attributes. The solution is inserting an intermediary entity in the middle, creating clean one-to-many relationships. Database architecture is the art of simplifying complex relational webs into linear, machine-readable paths. Data architects must map out these entities, attributes, and relationship fixes before a single line of software code is written. They achieve this using an Entity Relationship Diagram, or ERD. It serves as the universal blueprint for designing database environments. ERDs strictly document logical relationships, independent of whichever specific DBMS software a company ultimately purchases. Within the industry, the Chen model and information engineering are the two primary ERD notation styles used to draft these blueprints. In the Chen model, a standard entity is represented by a solid line rectangle. To denote a weak entity, the system uses a specialized symbol, a double-bordered rectangle. These specific geometric symbols act as a universal cross-platform language, allowing business analysts and data architects to communicate structure flawlessly. The true value of business data is determined entirely by how strictly and logically it is organized. By translating a messy reality into distinct entities, defining precise attributes, and engineering solutions to structural bottlenecks, architects build a functional environment. This level of planning results in a relational database that functions as a reliable central source of truth, routing information to high-level business intelligence operations. A properly designed relational database is the mathematically disciplined engine that makes modern business intelligence possible.